and thank you for joining us today. My name is MD Anisur Chowdhury. This work is done together with Pratham Patel, Shahajada Jawar, and our Honorable Professor Dr. Kefei Wang. We all from Gannon University, Erie, Pennsylvania. Today, I want to talk about a big problem with AI math solving and a simple but powerful fix we built called S2C, which stand for uh, Synergistic Self-Correction. This idea is simple. What if we could teach an AI to check its own works just like a student who review their answers before handing in test? Let's start. Here, the problem we are trying to solve. Right now, where an AI solves a math problem, it goes straight from the step 1 to the final answer. No stopping, no checking. If it makes one small mistake earlier on, say in step 2, everything after that is wrong. Step 3, step 4, and step 5 all broken, even if the rest of the thinking was perfect. We call this is the cascade effect. No early One early mistake causes a chain reaction of wrong answers. Think of it like building a house on a cracked foundation. No matter how well you build the walls and the roof and whole structure is unstable. The fixed, the AI needs to pause, check its own works at the key steps before moving forward. That's actually what our framework does. Now, other researchers have tried to fix this problem too. Let me quickly compare the existing methods. Chain to chain to thought as asks the AI to slow its steps. It's cheap, but the AI doesn't actually learn from mistakes or get master over the time. Self-consistency runs the small problem many times and pick the most common answer. It gets better result, but it uses 10 times more computing powers. That's very expensive. Process supervision does improve the AI, but it needs human expert to review every single step. That doesn't scale well. Our framework's S2C is different. It's improved the AI, it learned from mistake, it need no human reviewer, it is use only 1.6 time of normal computing power. In short, S2C gives you the best result at low cost. So, how does S2C actually work? We, we split the problem solving process into three stages, each stage with a clear job. Step 1, the generator. Solve the problem and highlight the most important steps, the ones where a mistake would really hurt. Stage 2, the critics look at look at those highlighted steps and try to find mistakes. It acts like a strict teacher looking for anything that's wrong. Stage 3, the synthesizer takes the critic's feedback and fix only the broken part, keeping everything else that was earlier correct. Together, these three stages from a loop: solve, check, fix. That's the S2C framework. Let's look at step 1 more clearly. In generator, does two things at once. First, it solves the math problem step by step. Second, it flags the most important steps, the ones must be right, that must be right for the whole solution to work. We call it critical point. This in the example on the slide, the generator is solving a speed and distance problem. It makes two key calculators as critical points, computing the total distance and then computing how far it left to travel. Why this is useful? Because now we know exactly where to look for mistake instead of checking the entire solution from scratch. The next stage can zoom in on just those flex steps. It makes checking faster and much more focused. Stage 2 in the critics, and it is its jobs to find problems. The critics look at the full solution and focus on the critical point that are flagged. It is trained to assume something might be wrong and to actually search for it. It looks for four type of mistakes: the wrong calculations, broken logic, missing step, bad assumption. In our example, the critics find that one of the flags steps has an undefined variable like cow, KAU, that makes no sense in context. It it uh, it then writes a clear report explaining what wrong and what the correct value should be. This report is what the next stage uses to fix the problem. Stage 3 is the synthesizer. It fixed the fixer. It read the critics report and produce a correct final answer. The key point is that the synthesizer doesn't rewrite everything from the scratch. It works surgically. It finds the broken step, replace it, and leaves everything else untouched. Think of it like a surgeon repairing one bandaged part without touching the healthy tissue around it. It carefully approach means the synthesizer only introduces a new mix in around 5.6% 6% of case. Most of it fix the problem clearly without causing new one. Now, how does we train S2C to do all this? We use three phases of training, each each building on the last. Phase 1, learn the structure. We showed the model many examples of the three-stage process. It learns the format, how to generate, critique, and synthesize by starting solutions from GPT-4. Phase 2, practice with a reward. The model practiced solving problems and get rewarded when it find answer was correct, like uh, drilling math problem with a simple right wrong gate. Phase 3, learn what makes a good critics. It is the most important phase. The model learn which critics actually lead to better answer and which one doesn't help at all. Each phase made the model smarter in the different way, and together they build a system that can genuinely self correct. Let me explain the phase 3 in a bit of more detail because this is that makes S2C special. In phase 3, the model only get a rewards from its critic if the critic actually fixed a wrong answer, not not if it sounds smart, not if it polish uh, polish, only if it worked. This is a very strict rule, and it's international. Uh, international. It it focused the critic to be uh, genuinely useful. If the critic gives uh, vague or unuseful feedback, it gets no reward. It is only paid for feedback that makes a real difference. The prevent that the prevents the model from learning bad habits like writing critiques that sounds good but not actually help. The reward is also balanced. 70% goes towards getting the right final answer and 30% towards right to fully critique but matter. Now let's look at the result. We tested S2C on a well-known math uh, benchmark called GSM 8K using a, um mid-size AI model with 8 billion parameters, not not a giant expensive model. The standard approach get 31.2% of questions right, but S2C get 49.9% right. That's a 60% relative improvement, and it's statistically significant. This result was not due to luck. And remember, we did this with a normal size model, no human reviewer, and low computing cost. That that's the real achievement here. Let's also talk about cost because actually uh, alone al- uh, alone doesn't tell the whole story. Self consistency, the method that runs the same problem many times, uses around 2470 token per problem, very expensive. S2C only about 400 tokens per problem, 84% less, where while getting better accuracy. When we measure accuracy per token, Basically, how much intelligence you get per dollar or for compute. S2C is nearly 8 times more efficient than self-consistency. S2C is not just smarter, it's smarter and cheaper. That's a rare combination. We also run tests of figure out with parts of S2C matter most, starting from the 31.2% baseline, adding the three-stage structure along give plus 6.6%, adding uh, rein, in, reinforcement learning practice give another plus 4.6%, adding the critic reviewer give the biggest jump, which is plus 7.5%. The critic reviewers is the single largest drive for performance. We also test what happen when we uh, remove pieces, taking out the critic and entirely dropped performance by over 10 points, removing the critical point flagging dropped it by over 5 points. Mm, the lesson the lesson, even uh, pieces of S2C is doing real work and simply asking an AI to check its works without this structure doesn't work. The architecture and the training together are what make it effective. S2C doesn't fix all error equally well. Does Let's break it down. Calculation mistake like wrong uh, arithmetic are fixed at 78% of the time. The synthesizer just recalculate from the error point. Missing step are fixed at 71% of the time by in, inserting the logic that was skipped. Logic error, flow, uh, float reasoning are fixed at 65% of the time. The hardest category is conceptual error where the AI completely misunderstood what the problem was asking. Those are fixed only 42% of the time. This is a known this is a known limitation where actually working on. Overall, S2C is very strong at uh, catching and fixing variable mistakes, which makes up the majority of the error in maths. One of the most uh, exciting findings, S2C gets more valuable as problem getting harder. From simple one or two step problem, S2C improve actually by 18% relative to the baseline. From the moderate problem like within 3 to 4 steps, that grows up to 57%. For example, problem with 5 or more steps, the ones where uh, uh, cascading error causes the most damaged, S2C improved actually by 239%. The baseline get only 10.1% 1% right. S2C get 38.2% right. This makes sense. The more steps is in a problem, the more chances of an early mistake to the ruin everything. S2C's loop is building exactly to handle this. Check the mistakes early, fix it early, and keep going. Let me warm up with the biggest picture. S2C uh, proves two important things. First, AI can learn from uh, learn to verify its own work without needing humans in the loop and without needing to a massive expensive model. Second, the three-stage problem is transparent. You can see the initial solutions and the flag steps, the critics and the final fix. For applications where, trust and explainability matter, like healthcare or finance, and the, these kinds of audit trial is very valuable. Look ahead, we believe that this framework can go well beyond math. The same the same generate critic synthesize loop could work for code debugging, scientific reasoning, and even legal analysis. Any domain where structured step-by-step thinking matters thinking matters. If you want to read a full paper or try to code yourself, please scan the QR code shows here. Thank you very much again. I am happy to answer all of your questions which you have on this paper.